All right, hello, my name is Sonu. I'm currently a senior studying aerospace engineering at RPI.
My name is Mei Mei, and I'm a junior studying chemical engineering at RPI.
And today we'll be talking about how GPS works. So it's a little bit different to how GPS is when you're familiar with your phone, or maybe GPS in your car. So we'll talk about the differences on how GPS actually works, the big system that runs GPS, and how it works in general. So here's a roadmap for the presentation real quick. First, we're going to talk about the history of GPS, how GPS was founded, why it exists, and how it was used in the past. Then we'll talk about the math and the science behind it. And we'll finish off with how GPS is used today and where it's going in the future. But first, let's start off with some history.
So, as you may know, the Cold War played a crucial role in pushing the technology for GPS. The first example was Sputnik in 1957, and this was a very basic version, and it was just based on radio signals. And it was also used for submarine missiles, and it was pushed by civilian safety. Up until that point, till about 2000, GPS was mostly used for military, but then the US developed a technology called Navstar, and this would be used more for civilian uses. And nowadays, as you know, GPS is used for civilian and military. Anytime you get in the car and you're using maps, you're using GPS. If you ever heard the app Life 360 to track location, that's GPS. And it's, again, still used in military. Okay, now that we've talked about the history of GPS, we're now going to talk about the science and how modern GPS technology works to bring everyone precision location.
So one misconception about GPS is it's not actually the little chip on your phone that's GPS or the chip in your car. It's actually an entire system of satellites that orbit around the Earth that give us GPS signals as they work today. And these satellites really work on one basic equation. So you've got the equation down here on the bottom. It says the speed of light, so the speed of the signal coming from the satellite, times the travel time of the signal, so how long it takes for it to get from the satellite to your phone or the satellite to your car, is equal to the distance from the satellite, so how far away you are from each of these satellites up in the sky. And we'll talk about why this is important in the next slide. So GPS signals and GPS systems work on a system called triangulation. They're based on a mathematical concept called triangulation. So the way this works is that you need at least 3 satellites to figure out exactly where you are at any point on the Earth, right? So if you have your location and distance from satellite 1, you can draw a circle around it that's equal to the distance we calculated in the previous slide. Then you have a second satellite that intersects with the first circle, so you have 2 points where the circles intersect. And then finally, you have a third satellite. If you get a signal from that third satellite, you have a third signal and a third point you can have where all 3 circles intersect, and that'll be where you are on the Earth. So we have a quick demo here. If we have the Earth, we have our first satellite up here in red. It casts this signal that goes to your phone, let's say your phone, your car, your laptop, whatever it might be. Then you have a second satellite that casts this signal to your phone and your laptop. You can see here, they both intersect at one point here. And then if you bring in a third satellite, this green one up here, it'll cast this signal, and you'll see that we're at this point on the Earth. So here's a really good kind of visual video example of how this works. Obviously the Earth is solid, so you're not going to get signals from every single satellite up in space all at once. So really when you're at a point on Earth, let's say this blue point spinning around here, you can only see the satellites that are, for example, in black. And the ones in red could be on the other side of the Earth, they could be blocked by something, so those won't be giving you signal. So that really shows how many satellites we do need up in space to make sure we have a good GPS signal at all times. But really one big issue with this is something called error. Right? The atmosphere is not perfect, science isn't perfect, our machines aren't perfect, so we have to calculate that and make sure that we don't have as much error as we can possibly, so that we can have as little error as possible. So one really big source of error is the atmosphere. The atmosphere is kind of like this big thick soup that surrounds the Earth, and that really slows down our GPS signals and makes that equation that I showed you guys earlier really difficult to calculate because it's not actually that simple. The atmosphere brings in a lot of discontinuities and really complicated math into the equation.
But let's simplify it and talk about the science that we can understand, like the Doppler effect. I don't know if anyone's heard of that before. It's something like when an ambulance goes by and it goes woo, and it stops like that. So the Doppler effect is defined as the change in a wave as it moves towards or away from an observer in place. And you can see, as I was mentioning, the ambulance going by. You start with the observer has a lower frequency and then moves to higher frequency. And there's actually a mathematical equation we can use to solve for this. So it is to find the observer's wave frequency, your F0 or F0, you can see on the left of the equation, you have to add the velocity of the wave with the velocity of the observer and then divide it by the velocity of the wave plus the velocity of the wave source. And then you multiply that all with the wave frequency. So the Doppler effect is really important because that's what's happening all around us, and it was the basis for early GPS technology, like Sputnik, as I had mentioned before. So you can kind of see it here, traveling all around. So now that we understand the sciences of GPS, we're now going to talk about the modern applications for GPS.
Right, so like we mentioned before, GPS was really a military technology at first, but like many things, for example the microwave, which is also a military technology at first, it eventually trickled down to civilian use. The US originally set it up back in the Cold War to help track soldiers out in the battlefield, and it really made an important effect on not only the Cold War but any wars after that, because it's really important to know where your soldiers are in relative to an enemy or a threat. But of course these days GPS is a lot more common in our phones, in our laptops, in our iPads, in our cars, whatever it may be. For example, here's some useful ones. You have your Find Your Friends app, maybe on your iPhone or whatever. Grubhub when you're really hungry at night and you don't want to go outside and get any food. Google Maps, super useful, for example when you're driving, I use it all the time. And then Snap Maps, so you get to stalk your friends on Snapchat. But let's talk about where GPS is going in the future. So GPS is really important these days in self-driving cars. It's really important we have a really good and accurate GPS signal when designing self-driving cars, because when you're on that really small scale of being in a lane or out of a lane where a lane's maybe only 10 feet wide, you have to really make sure your GPS signal is accurate enough to really realize where exactly you are on the road. You don't want to be on this exit over here, you actually want to be on this part of the road. You want the computer to realize that you're here, not there. And especially when these cars are eventually going to take over driving for us, it's really important they're as accurate as possible. So yeah, thank you. Alright, so now we're going to move on to a hands-on activity, and this is based off of the board game Clue, if you ever played it. Here's our board right here. And really the point of this is there's been a murder in this house, and we're going to use some of the technologies we talked about while talking about GPS, mainly triangulation, and get to where the murder happened and figure out who did it. So we've got multiple suspects who have been accused of this murder, who have been in the house at the time, and using triangulation, using these distances, we're going to figure out exactly where they were in the house at any given point. So should we start off with Colonel Mustard?
Sure. So Colonel Mustard, at the time of the murder, was 2.5 inches away from the billiard room, and he was 4 inches away from the lounge and 2.5 inches away from the conservatory.
All right, let's start off with the first one, 2.5 inches from the billiard room. So like we talked about in the GPS presentation, we're going to use triangulation and help draw those circles you saw in the presentation and try and figure out exactly where Colonel Mustard was. So we've got our tools here. We've got a ruler, a compass, and some highlighter markers to make it clear which character is which. So let's start off with that 2.5 inch metric, right? So we're going to take our compass, move it out to 2.5 inches, so kind of measure it out. Right about there. Oops. All right. So he was 2.5 inches away from the billiard room. So let's just put our compass right in the middle of the billiard room and draw a 2.5 inch circle. All right, that's as far as it really needs to go. And let's make this, I don't know, yellow so we can highlight that this was Colonel Mustard. Do my best and try and shade this in. Cool, we've got our first circle. Let's also just mark down that Colonel Mustard is yellow, just for reference. Okay, the next one was he was 4 inches away from the lounge. So let's do the same thing. Get our ruler, bring it to 4 inches. And do the same thing from the lounge. So just kind of rotate the compass. And then let's also color it in like last time. All right. And our last clue, this is going to be, I guess, in effect, the third satellite in our GPS system, is that he was 2.5 inches away from the conservatory. So let's bring this compass back to 2.5 inches. Measure it out. Just move that a little bit. Right there. And that was from the conservatory. So, all 3 circles. You can see it's a little bit of error. We've zeroed down on Colonel Mustard being in the ballroom at the time of the murder. So just draw a nice big star.
So I can take over for the next one. So our next suspect is Miss Peacock. And Miss Peacock was 4.5 inches away from the library, 4.5 inches away from the ballroom, and 2 inches away from the hall. So we're just going to do the same thing that Sonu did. We're going to take it 4.5. And then that was from the library. So we're going to find the library on here. All right, and we'll make her color green so we can see the difference. Okay, and then our next hint was that she was 4.5 away from the ballroom. Just color that one green again. And then 2 inches from the hall, so we have to change our protractor. So we can see where the 3 intersect, and she was about in the lounge.
All right, let's move on to Professor Plum. Same process as before, so we'll just kind of go through it real quick. So let's set our compass to 4.5 inches. So it says Professor Plum was 4.5 inches away from the conservatory, so just adjust the compass real quick. 4.5, okay. So we've got the conservatory down here. We're just going to draw a nice circle again. Let's make him orange. Let's also go back and mark that in our little worksheet. So we've got he was 4.5 inches away from the conservatory, that's been done. He was 2 inches from the dining room. So let's get this. 2 inches right there. A little messy there, but that's all right. Try and trace that circle. Great. And we finally have that he was 5 inches away from, a little blurry. He was 5 inches away from the hall. So let's take our compass, again, set it to 5 inches. And we've got the hall right here at the top. Just from looking at it, you can kind of see all these lines end up intersecting in the kitchen. So we know the murder happened in the kitchen, and it might be Professor Plum, but let's just try doing Miss Scarlet just to make sure.
So we know Miss Scarlet was 5.25 inches from the conservatory. just take the ruler. .25 from the conservatory. So we'll make her pink. And then our next hint was that she is 3 inches away from the dining room. Okay, from our dining room. Oh, sorry about that. And lastly, that she was 2.75 inches away from the library. Okay. So as we can see, her 3 lines intersect in the hall.
All right, let's make some conclusions here. So as we found out originally, Colonel Mustard ended up being in the ballroom, so just write that down real quick. Miss Peacock ended up being up here in the lounge where all 3 of the green lines intersected. We saw that Professor Plum was in the kitchen, so a little suspicious there. And finally, Miss Scarlet we found out was in the hall with these pink lines. So from all this we can conclude that Professor Plum was the murderer because he ended up being in the kitchen at the time of the murder, and the murder happened in the kitchen. So yeah.
So thank you for listening. I hope you enjoyed learning more about GPSs and also getting to do the hands-on activity. And if you want to find out more information about engineering ambassadors, you can find us on these sites. So thank you.
Thank you.